All right, so for lesson 2, we're going to be looking at what's called algorithm efficiency. So before we really get into this, having some scrap paper and something to write with just makes it easier to work through some of the examples instead of just watching the video. It's nice to actually do some of these examples. Small scraps of paper, post-it notes, half a note card, halves of note cards are all fine. Just something quick and disposable, or recyclable, I should say. Um, and the idea of it is, if we have a list and we have numbers. So for example, let's say we had raffle ticket numbers and we were trying to see, hey, here's the number we pulled. Did anybody have that number and win? So here at the bottom are a list of numbers that people have. Here's the number we're looking for. And we want to figure out what is an algorithm that would allow us to search the list of possible winners to see if anybody has 705. And we have to think of this like a computer program in that it has to be step by step, and it has to be a finite number of steps. So take a minute and just kind of think about what is one way in which I would describe looking through this list of numbers to see, does anybody have 705? In other words, is the number 705 in this list at the bottom? And if it helps, pause the video for just a minute while you think through that. So, possible algorithm. You start with the first element. You look, is the number I'm looking for equal to this element? If yes, we found our number and we can stop. If no, we go to the next element and repeat these steps. And in other words, we check every single element and see, is this element 705? Is this element 705? Is this element 705? Is this element 705? If we reach the end of the list and none of them are 705, then nobody has 705 and nobody's won the raffle. This is what's called a linear search. And it's called linear because the length of the search is always going to be equal to the number of elements in the list, because we will always check the entire list. So if I had 3 elements, there are 3 steps to that algorithm. If there are 6 elements, I have 6 steps to it. If there are 10 elements, there are 10 steps to it. If there are 100 elements, there's 100 steps to it. So that's nice and all, but what if we're dealing with massively large data sets? What if we were looking for one number out of a list of 10 million? Now we're getting into numbers that, while doable, start to get kind of big for an algorithm. So the challenge is, can you come up with an algorithm, a different way of looking through that list? And I will even go so far as to tell you, the list is sorted so that the numbers are from smallest to biggest. You can start at any of the sticky notes, so you don't have to start at the first element. You can start at any element. You don't know what the element is, but you can start at any position. You're allowed to jump over elements, so you don't have to go through them in order. You can determine which sticky notes to search based on what you're looking at now. And so think about this, because this is challenging. Take a minute or two, see if you can think of a different way besides the linear search to see if 705 is in that list. Pause the video, come back. All right, so here's an algorithm I want you to try. So you have your list in front of you. You want to find the middle number in the list and compare that to the number you're looking for. So you want to find the middle number and compare it to 705. If the number is less than the given number, remove all of the numbers to the right, including the middle number. If the number is bigger than the given number, remove all the numbers to the left, including the middle number. Then find the middle number in this shorter list and repeat. Find the middle number in this new shorter list. Repeat again. And then you should have found your number. So to kind of show this visually. So here's our list of numbers from smallest 117 to biggest 833. We're still looking for 705 there at the top. We want to take the 705 and compare it to the middle number in this list. My middle number is 410. So I want to compare. Is that 705? Are they equal? The answer is no. 410 is smaller. In other words, the 705 is bigger, so I'm going to keep everything bigger than the 410, which is the right side of my list. From 410 to the left is getting removed. So I now have a new list that only has 3 elements in it. I'm going to compare the 705 to the new middle element of 716. Is 705 equal to that? Bigger or smaller? Well, 705 is less than that. So I'm going to get rid of everything from 716 right and keep everything that's to the left, which leaves me with just one number. And now I compare 705 to this number. Is it equal, bigger, or smaller? It's equal to it, so there is my number. Notice that only took me 3 steps. This is what's called a binary search. And the next few slides explore why we call it binary. It is a faster way to go through a list and search for something as long as our list is in order. So if I only have 1 element in my list, I only need to take 1 step to find something. If I have 3 elements, it takes 2 steps. If I have 5 elements, it takes 3 steps. And we're already noticing this is a little different from linear, because in linear, if it was 5 elements, it took 5 steps. If there are 7 elements, it takes 3 steps, what we just did. 9 elements takes 4 steps. But even 15 elements I can do in only 4 steps. So if I graph this and compare it to then why is it that it's taking so much fewer steps? Why are we being called binary? Is let's look at how many bits it takes to represent the different number of possible, the different number of elements that I have. If I have 1 element, that takes 1 bit. So it takes 1 step. Anything from 2 up through 7, I'm sorry, 2 and 3 are 2 bits, so it takes 2 steps. 4, 5, 6, and 7 all require 3 bits, so it takes 3 steps. 8, 9, 10, 11, 12, 13, 14, 15 all require 4 bits, so they take 4 steps. 16 through 31 elements in my list would take 5 bits to say those numbers. It would take 5 steps. This is why it's called binary. The number of elements I have in my list, it's called binary because the number of steps is how many bits it would take to write that number of elements. So linear, doable, but the number of steps will always be however many elements we have in our list. Binary is a faster method as long as our data has already been sorted. So binary is considered more efficient if the data is sorted. If the data is unsorted, that's a different problem. Please note how I used problem there, like we defined it. It's a different problem because we then have to take into account, well, how efficient is it to sort the data and then do binary versus just doing a linear search? Because linear, it doesn't have to be sorted. So efficiency is how many steps are needed to complete an algorithm. Linear means that we search an algorithm by checking every single element in the list until we found it or we've checked all of the elements. Binary, we have a sorted list and we check the middle of the list, remove the half that are what we're looking for is not occurring in, check the middle of the new list, remove half it's not occurring in, and we keep having the data till we found what we wanted or we've gotten rid of all of the data.